All right, we are recording. Should have waited before I started recording. Okay. So for those of you just joining us, not you guys, this is my solution to problem number 3 on the exam. And if you need to, pause it, study it, and hopefully it'll make sense to you. I'm not quite done with it though. We've found the area function. And so now we know to get volume, we just need to integrate it. Well, I'm going to pull the constant out. The solid exists from 0 all the way out to 3, the way it's described. And then we do 3 minus x squared dx. This is a 14-point problem. I didn't say it here, I did say it later on the exam, but finding an integral that will do the job, that's going to get you most of the points, maybe 10. I think on the last problem on the exam, I think I told you exactly 10. Find me the integral. You get 10 points and then 4 more. But when I wrote this problem, I thought, well, this would be a fun one to evaluate. So I asked you, not just to find the integral like I did on most of the other problems, but to actually find the value. So there are 2 ways to do it. One way is it's slightly more clever maybe, and that is not to square it out. That's a mess. That's going to create a ton of arithmetic. Well, maybe not a ton, but 100 pounds of arithmetic maybe. The best way is to look inside that square and say, okay, 3 minus x. What's the derivative of 3 minus x? -1. Yeah, a constant. I can get it. So I'm going to substitute. I'm not going to write out the details. This minus, like I need a minus to be the differential. And then I cancel that minus out, so I'm actually multiplying by +1. Everything's good. And then all I have to do is raise the power. Divide by the new power. And go from 0 to 3. So that gets me -pi/24. 8 times 3 times 0 minus 27. 3 cubed. Right? And that simplifies to 9 pi divided by 8. And that's what I was looking for. And I saw it on one paper. Now, there's another way to do this problem, which, and some of you maybe did this, and I didn't really think about it until today. So if you think you did this, let me know, and maybe, you know, you can get more points. I described the solid for you, but I could orient that solid however makes the most sense. Like I want to get the volume, and I want to get it like without having to do a tremendous amount of work. Okay, it's a sign of, I guess, sort of intelligence. If we can do it, get what we need, and not have to work harder than we need to. And so what I can do is sort of flip this triangle around. So the big cross sections would be out here, and they would come down to 0. I think you can see we can make that work. Convince yourself it's going to be the same solid. So now the point 33 is up there. Does that make sense to you? Yeah, and then the area. What's the equation of this line? X. Y equals X. Nice and easy. So if you give me an X value here, then the area, we still have semicircles. So I'm going to take X divided by 2 and square it. It just simplifies things just a tiny little bit. And I remember seeing the function x squared and thinking, well, that's not right. But then after I graded it sometime this week, I discovered, well, it could be right. If as long as you got everything like twisted for this new perspective. So if you think you did that, let me know. And maybe, I can make an adjustment. I think a lot of people, because of the r squared here, they just plugged an x in there and maybe didn't really know why they were doing it, but they knew they didn't want an r in there and we needed an x. But if you really did it because you're thinking, let's take this guy and let's just reorient, make the problem as easy as possible, let me know and I'll reassess your work. All right. Most of the rest of the problems on the exam, a good chunk of people got them exactly right. I don't feel a need for us to like really take a long, hard look at some of the problems. But you individually, if you have questions, come and talk to me. I can Zoom with you if you would rather, or you can come to my office. Matthew was in this morning and it's a nice, comfortable office, right? And there's room for us to work and a nice big whiteboard if we need to use it. Okay. And if you have any other questions on the exam, just let me know and talk about it. And remember, you know, maybe some of these problems will be on the final, problems like it. So I think we ought to have another cross-sectional area problem on the final, just because I think we need more practice. We'll see. There is actually a homework assignment I posted on Friday, but Matthew told me I made it be due in June. Like, why would I do such a thing? Like, well, don't answer that question because I don't want to hear it. I didn't mean for it to be due in June. And since it was due in June, it didn't show up on the calendar unless you scrolled way out into the future. But I fixed it, and now it's due on Friday. So normally assigned on Friday, with no class on Monday, it'd be due on Wednesday, but because, you know, maybe I messed up, you didn't see it on the calendar, it'll be due on Friday. And I think some things I'm going to say at the beginning of class might help you with those problems. You know, they're kind of messy, but they're kind of fun too. Like, there's a lot of stuff to do, and make sure we can do it exactly right. And when there's a lot of stuff to do and you do it and you type it in and you hit enter and it shows up green, like, isn't that an amazing feeling? So give it a shot. And like I said, the first thing I'm going to do is kind of related to those. Remember, in section 3, we are taking algebraic functions whose antiderivatives we don't know. We're converting them to trig functions. Okay, I think I said on the video, it may seem like a bad idea. Like, what we want to do is avoid trig functions because, I don't know, maybe we're not as comfortable with them. And here we're doing just the opposite, but you could see how it works out and it would make some amazing results as long as we're careful and we work it all the way back. And so what I want to do at the beginning of class is talk about some more trig integrals. I think I said in the video that presumably we're experts over section 2. So if we can take a new one and convert it to section 2, then since we're, you know, experts, we can get the antiderivative. But I didn't actually prepare you to be an expert. So there are kind of a couple of examples I'd like to talk about. Maybe the homework will run into them. And in section 3, you convert it to section 2, and maybe we haven't quite covered the bases. I want to talk about some that can show up there just so that we can better handle more antiderivatives. So I have just a list of things. The first one I want to talk about, actually, I want to use theta. That's our preferred variable for trig function. Maybe this showed up in Calc 1, the antiderivative of secant. I don't remember if we talked about it. I don't remember that we did, which means maybe we didn't. And so I want to talk about it just briefly because I think we're going to run into it again and we want this to be equipped for it. Now, how do we find the antiderivative? Well, what we need is like a genius insight. Okay, like some super creative person, not me. I just copied that creative person. Okay, came up with this idea, and let's follow through and see why it's a good idea and how it's going to help us. So this super creative person said, look, just multiply by, I think I want to write tangent first. Tangent theta plus secant theta divided by, of course, same thing, so that I'm multiplying by 1. And while it looks actually a whole lot worse, it's the same thing. Multiplying by 1 doesn't change anything. And then let's multiply that numerator out. Secant theta tangent theta plus secant squared theta divided by tangent theta plus secant theta. No, I got it backwards, but that's okay. So why does that help? Yes, Noah.
You have a secant squared theta now?
Correct. That's crucial. I'm not sure that tells me the antiderivative, but it's an important step. What else? Who sees? What would you substitute for? Scott.
Would it just be secant you substitute?
If I let u be the secant, then du is secant theta tangent theta. So I could plug a u in here, and I could make this guy with the d theta, but I have a u squared here, but it's not multiples. So it's a good guess, but I think it's going to quite work out.
Could it just be the whole bottom then?
The whole bottom, why?
Because it'll get you the same derivative from that
Yeah, what's the derivative of the bottom?
top.
The top. So whoever came up with this idea, not me, probably 150 years ago, they saw we can make the derivative of the bottom show up on the top. You see how it works? Derivative of tangent, secant squared. Derivative of secant, secant theta. Theta, secant tangent. The derivative of a sum, the sum of the derivatives. So if I let u be secant plus tangent, then this becomes 1 over u du. And the antiderivative is of 1 over u du? Pardon? ln u. ln. So here we have it. And tangent plus secant can be negative, so we need absolute values in it. And well, plus c for good measure. It's tricky, but true. Okay, we talked through it, but basically if we substitute for the bottom, we get that, 1 over u. The derivative of the bottom is on the top. Okay? So, earlier in section 2, I asked you to memorize a couple of antiderivatives, right? Sine squared and cosine squared. They're very similar. And you had a chance to show me that you took me seriously on the exam. And most of you did exactly right. It was pretty easy points for most of you. This one is somewhere between, like, we're never going to see this again and memorize it. So we're going to run into this every now and then. It's not quite as big a deal. It's sine squared and cosine squared, but I'll just say, take note. And we'll put this in our back pocket. And if we ever discover the need for it, we'll pull it out. We won't go through the argument. And I'll say, remember, on February 19th, is that what it is?
17th.
Yeah, 17th. We found the derivative of the antiderivative of C. All right, next up, secant cubed. Why did I skip over secant squared? Because its antiderivative is Tangent, yeah, we know it. We've known it for a long time. No mystery there. This secant cube is a very interesting one. You can just, like, so when calculus gets interesting for the professor, it gets maybe sort of scary for the student because they can imagine, like on the homework or test, what's this going to look like there? So if you can just free your mind up from worrying about that and just go along for the ride here, there's something really fun that happens with this integration problem. And it's probably not very intuitive, so it's going to lead us through it. And you know, when we get to a place where I think you maybe will help me out, I'll ask for questions. But when we're not there, I'll just kind of lead us forward. The first thing I'm going to do is not obvious at all. I'm going to do it by parts. Okay? I don't think that would like jump out like, oh yeah, let's do this one by parts. But that's what I'm going to do. And so I'll ask you to help me. How should I break it apart? Like, I got to be careful what I put on the DV, because to find V, what do I have to do with it? Integrate it. So think about that for a minute. What would be a really good thing to put on the DV? And good means we know it's antiderivative. Secant squared, absolutely. Theta. And that means U is everything else, which there's only one more secant, and then we say du, well, that's secant theta tangent theta. And what is V, Matthew? I think you told me, didn't you? No, you told me what to put on it,
Yes.
because you could see that we would know V then. See, I have these three powers, I can split them up however it feels right, but you think, man, what do we have to do with those? We have to, whatever we put on the DV, we have to know it's antiderivative. I could have put secant there because we just worked out, just in the nick of time, what its antiderivative is. But it makes more sense to put secant squared there because we get such a pretty V. Instead of having this thing there, we have just tangent, that's all. Okay? So this is, we remember our biparts formula, UV, tangent theta, secant theta, in some order, minus the integral, the trade-off integral, du, which is secant theta, tangent squared theta, d theta. That's good. Follow? Am I doing it right? How do you think we should attack secant theta tangent squared? Somebody give me a good idea. It's like a section 2 integral. And throw something out. Whether you can see it's going to work or not, tell me something I can do.
You substitute for it.
That's a, we should always be thinking about that. Is there a substitution that's going to give me what I need? If the square was on the secant, then like that's an easy substitution. Just let U be secant, and then there's du, tangent, sorry. Yeah, let U be tangent, and there's du, secant squared. So, but I can't quite work out a straight substitution when the square is on the tangent and not the secant. And, you know, maybe if we would think long and hard, we could come up with one, but there's something else I want to do. So it's like if you don't know what else to do, like use an identity. Know what?
You convert it to secant is 1 over cosine tangent sine.
Oh yeah, and probably on the video you heard me advise you to do that. Like if you can't get it with tangents and sequence, take a look at it in sines and cosines, which you can always do. Okay, that's super good advice, not just because I said it, but because Noah reminded. But I'm not going to do that here. Okay, we could, I'm not going to. And the way this works out, I want to remind ourselves, this is where we started. Secant cube theta, And what we got is secant theta, tangent theta. And what I'm going to do is replace tangent squared with the Pythagorean version of it, which is secant squared theta minus 1. Pythagorean identity. Okay. And let's see where that takes us. Good there. I'm going to keep bringing the secant cube down. You'll see why. And then I'm going to break this into two integrals around that minus sign. So let me just write them out. That's the first one. And then for the second one, I get minus minus, so I'm going to get plus secant theta. So when we do by parts, we trade off the original for a different integral. And we hope that we can find the antiderivative on this trade-off. Well, this one's hard, but we're not giving up. So, well, let's write it like this. Well, it still doesn't quite help us. Let's write it like this, and we'll see what we can get. Jesse?
I didn't see the negative.
Okay, you're good now. David? Yes. Isn't that slick? What do we do with this guy? We just figured it out. Right? Write it in. And then David, so this is like, feels like almost like we're cheating, like we're going to find the antiderivative indirectly. I'm going to add this integral to both sides. How many do I have on the left? Well, right now there's one. There it is. If I add one to it, how many do I have?
2.
I want to have 2. How many are going to be on this side? None. I'm adding it across. So we get here 2 integrals of secant cube is equal to secant theta tangent theta. That piece has been patiently waiting for us. Plus the integral of secant, which is right there. And so to solve for this guy, we just need to divide by 2. I'll just write it 1/2 times the whole thing. And now we'll say plus C. We're done. This is an absolute balance. Okay. So an interesting thing that can happen with integration by parts. If you had AP calculus in high school, you've seen it happen with other examples as well. This sort of thing where the integral we're trying to find just happens to show up. There's another way I could attack this problem, and it will lead me to this integral, but it's going to have a plus sign. Like, that's no good at all, because then I need to subtract it away, and that on one and the other side goes away too. It's like I'm spinning my wheel. I did a bunch of stuff, and it didn't do me a bit of good. But this is the way we did it, and we got a minus sign in front of it. We can just add it across and then divide by 2. It's super slick way. And I think we're going to run into this again. I'm not going to say memorize it. I'm going to say memorize that we did it, and you can find it somewhere in your notes to class, or maybe you can write it somewhere in your notebook, and we'll pull it out when we need it. We're not going to waste brain cells by memorizing it. We're going to remember that we figured it out and we know what it is. All right. Let's do this problem. Are there any questions? Do you see how this works? It's pretty slick. I think I can assign a problem where the same thing happens on the homework. I'll see if I can find it if I remember. Let's try this problem. Find the length of the curve f of x equals x squared from x equals 0 to x equals 5. So you're probably thinking like, man, this is an abrupt change, going from these kind of abstract antiderivatives to a pretty concrete problem. But let's see if we can solve it. Anybody remember how to do it? How to find the length of a curve? Scott?
Isn't it the integral of the square root of 1 minus the derivative of x squared?
Plus.
Plus, yeah.
Yeah. Yeah, we have a formula. We worked it out in the last chapter. A to b square root 1 plus f prime of x. Squared. Remember? This function is a parabola. Opens up, and we're going out here to the 0.5, 25. You want to know how long is the curve? It's a little bit longer than 25, right? We just go from here to here, we would go 25 units, and we're curving a little bit. So let's see, f prime of x, what is it? 2x. And so the length is the integral from 0 to 5, the square root of 1 plus 4x squared. Square the derivative. So if you're watching on video, you may need to pause it and process the part of the screen that you could not see for a little while. Okay? Did we know an yeah.
What is the 4x squared instead of 2x?
So it's the derivative squared. What's the derivative of x squared? And square that. 2 squared is, pardon me?
Would that not be two?
So we're squaring the derivative. Four x squared. Right? Okay, now that's the integral. We could get an approximation from our calculators, but I don't want an approximation. I want to work it out. I want to find the exact answer. Okay, so tell me what to do. Do we know an antiderivative? Square root of 1 plus 4x squared. Will a simple substitution get it? By simple, I mean calc 1. So the answer is no. If I had an x right there, then yes. The derivative of the inside, what is it? 8x. If I had the x, all I need is the 8. Throw it in, divide by it, and we're good to go, right? But I can push 8s through the integral sign. I can't push the variable. There's no rule in calculus that says we can do it. So simple substitution won't do it. We don't know an antiderivative. We haven't seen it before. it looks a lot like the kind of learning in section 3, right? With a radical and a quadratic. But first, I'm going to deal with the 4. And because the radicals we looked at in section 3, none of them had a coefficient, or the coefficient was always 1. So we're going to do a simple little substitution first. And Jesse, this will make it feel good to you. I'm going to let you be 2x. Okay? This is a general technique we can do whenever the coefficient is not 1. Take its square root, the coefficient, and substitute, and then du, of course, is 2 dx. And then we get the integral square root of 1 plus what? U was 2x.
U squared.
U squared, yeah. So it looks like the kind we've been talking about. The differential, I need to divide by that 2. Let's push the 1/2 out in front. So now I have exactly a case 3 antiderivative from section 3. Because it's a definite integral, I can change my limits. So I don't have to substitute back, which is kind of a, I was going to say it's kind of a pain. But I don't want to say that because I'm the teacher, which involves some detail to write it back in terms of the original variable. And so, because we have a definite integral, we can just change the limits. So when x equals 0, what does u equal?
0.
0. When x equals 5, what does u equal? 10. Yeah, so we can change those limits, and now we're done with x. We never need it again. I'm going to focus on u from now on. So now we're going to replace u with what? For this radical. Case 3, Victoria's going for it. Did you say tangent? Yeah. Now you said some other stuff. Case 3, we let u be tangent theta. Our constant is 1. If the constant was 4, it'd be 2 tangent theta, right? But the constant is 1. And then du, secant squared theta d theta. And the radical becomes, I asked this, see if you could make this automatic. So when we see a trig substitution kind of integral, we make our decision and then boom, boom, those should be automatic. Got it written down somewhere. We don't derive it every single time. The third one is true because of the Pythagorean identity. I showed you in the video for case 1, and then I said it works out the same for all of them. Just trust me. So we're going to remember, and the way I remember it, tangent and secants kind of come together. If I put tangent here, I put secant there. This was actually case 2. Case 3, we put a secant up here and we get a tangent there, right? Because they're connected on that Pythagorean identity. When we put a sine here, case 1, we'll get a cosine. Again, through the Pythagorean. And so we get 1/2. The integral, the radical is secant theta. The du is secant squared theta. Again, we can change the limits. So we'll be done with u then. When u equals 0, the bottom limit, well, what angle is it whose tangent is 0? Tangent of pi over 4 is 1 because the sides have the same length, the legs. The tangent of pi over 2 is undefined. That's where it's shooting off to infinity. That's 0. The upper limit, I picked, originally I picked 5, which turned into 10 because of our substitution. We don't know the angle whose tangent is 10, but we know a symbol for it. And we like this better because we don't have to know. It's the inverse tangent of 10. Right, if u equals 10, tangent theta equals 10, so theta is the angle whose tangent is 10. And now let's clean this up a little bit. Integral 0 to the inverse tangent of 10, the arc 10 if you prefer. Secant cube theta d theta. Now what?
We already know the
We
answer.
just did work this out. And when I wrote this problem down, I said, well, what does that have to do with secant cube? Well, on surface, you couldn't really tell. But it showed up, and fortunately, we still have it written on the board. Okay? So let me bring this over, and I'll write it right below our antiderivative. Notice we have a 1/2 out in front. That's not this 1/2. And then we get our antiderivative, which is another 1/2 times secant of theta times the tangent of theta plus the log of the arc. Everything was positive. Well, we'll leave it there. I'm going to write a straight. I think I need a paren and then a straight line. We're going to go from 0 to the inverse tangent. Okay, 1/2 times 1/2 is 1/4. And then I get the secant of the inverse tangent. We're plugging it in. 10 times the tangent of the inverse tangent. That's just 10. Plus the log of the sum. That's 0, everything is 0. This wipes out the first term. The secant of 0 is 1. Tangent of 0, 1 plus 1 is 1, the log of 1 is 0. So nothing at the lower limit. One-fourth, almost done. We can pretty that thing up a little bit. Notice we have a trig function composed with an inverse trig function. Right? That's not a trig function, that's an algebraic function, remember? And so let's draw a picture of that, of the angle, the inverse tangent of 10. Here it is. And to have 10, we need like the ratio of the legs opposite to adjacent. We need it to be 10. The easiest way to do it is to pick opposite to have length 10 and the adjacent to have length 1. And then the hypotenuse, which the secant uses, is 10 squared plus 1, the square root of 101. So what's the secant of that angle? Secant is opposite of cosine. Hypotenuse over adjacent.
Could just be the root of 101.
Square root 101. Just a hair bigger than 10. And then our tangent of the inverse tangent of 10, those just cancel out. And then I get plus the log of the secant. We just said everything's positive, we can now agree. There's our answer. There's really no simpler way to write it. We can't break up logs over sums. There's no way. So That's our answer. I pulled my calculator out, and I think I wrote it on here. It's 25.87. Does that answer feel good to you? Yeah, we said earlier, it's got to be bigger than 25. And then just for the fun of it, I found the straight line distance. Like this. If you want to get from here to here, and you're like the sort of guy that goes like, no funny business, go straight there, you're just going to go on the line, right? But if you sort of person like me, you like to take the scenic route, kind of wander around, it's going to take a little bit further. We're going to follow this parabola. The straight line, of course, Pythagorean theorem. It's the square root of 650. 5 squared plus 25 squared. And the square root of 650, is it bigger or smaller than this number? Bigger. A lot bigger? A little bit? Well, I already gave it one. It's still 25-ish. 0.5. So the direct way, 25.5 units, miles, maybe. The scenic way, just a little bit longer, 25.87. Questions? So did it make sense? Jesse?
So the 10 that you have in there where it's like the root of 1, that's from the tangent times the tangent.
The tangent of, not times, of. Yeah. I mean, the way we think about this, the way I'm strongly encouraging you to think about this, which started last semester, is this is the angle whose tangent, I can put a 10 in there. That's the angle whose tangent is 10. Well, if I take the tangent of that angle, what do I get? If the tangent of that angle is 10, if that's the angle whose tangent is 10, then the tangent of it is 10. Sounds like a tongue twister.
The last thing that I didn't really understand was the 10 coming from the 5, like that step. I
Oh.
don't understand.
Is it still on the board? It is not. So we had, this was our original function, and it went from 0 to 5, right? And we made this substitution. So when x equals 0, u equals 0. But when x equals 5, 5 times 2, u equals 2. Yeah. So we're really fortunate that there's a definite integral. We can just change the limits and not have to fight our way back. When I was a Calc 2 student, I probably shared some of this with you all that were in my Calc 1 class. I went to the university on like an engineering scholarship, and I hated the university and eventually changed my major. But when I went to grad school, I went back to the same school. And I walked into the place where the graduate students are. And back in those days, like the professors would lecture 2 days a week, and then you'd meet with like a graduate student for a question and answer period. And the guys I had for my question and answer, Calc 1 and Calc 2, they were there. And so I said, oh yeah, I had you in Calc 1. And so one guy goes right over to a filing cabinet, pulls it open, and pretty soon he's got my final exam in his hands. It was a little bit humbling. You know, I was such a dumb little freshman. But on this technique right here, this will make you feel better, hopefully. The way we use these triangles to write these trig composed with inverse trig, when I was a Calc 2 student, I didn't know how to do that. And so I left all of my answers in the trig. And you know, they were correct, but not the best way to write it. So I lost a few points. But I learned from that experience. It's a good thing about making mistakes is it gives you a chance to learn from them. And hopefully we'll make that mistake. Any questions? We really didn't cover any new material, but you know, Friday after the exam, we kind of launched a new topic, and maybe it's a difficult topic, I don't know. I hope you'll think it's a fun topic. There's really stuff for us to do here. We've got to think, sometimes we're like following a formula and then we have to be creative. And it's good for us to think both ways. And we worked out a couple of results. One of them immediately came in handy, right? Secant cube. Like who would know finding distance on a parabola that what we need to know is the antiderivative of secant cube to figure that out. And like I said, we'll kind of remember, we're not going to memorize either secant or secant cube, but we'll know what they are. And we may not be so lucky that they'll be written right on the board, right where we need them in the future, but we'll remember them. All right, this is Wednesday. We will probably start a new section on Friday. And it's an easier section, I think. So maybe we'll be ready for that. See you then.